It is so nice to be here at the end of this magnificent 10-week conference workshop. And it was so much fun talking to everyone here. Like, I'm really, really grateful to all the organizers for sort of putting this gargantuan thing together and making it work. Thank you. I'm going to talk a bit about star formation histories today. I think some of you might have heard parts of this already, so I apologize for that. But the basic point of this is thinking of this question of when you, in your research, think of galaxies, how do they look, right? So we have heard many different perspectives from many different people. If you ask John and Mike and folks, right, like galaxies are these like pristine sort of treasure houses of morphological information that contain like a lot of, like the dynamics and the structure tell you about how they evolve. If you ask Christian or Howen or people who think of like either merger trees or galaxies as graphs, Johansson said this too as like the most natural representation. You can think of like dark matter halos collapsing over time and forming structure through that. If you think at the field level, like Sultan was talking about, then galaxies are just nuisance parameters that you marginalize over to get to the interesting parts. There's cosmology. And finally, I'm going to sort of talk about like the last of this, which is to think of galaxies as these evolving systems with time, and you essentially trace one quantity over time and then sort of see what imprints that has of physics, right? Where does it? No? Okay. I guess. All right. So before we move in, this is a galaxy star formation history. This is the primary quantity I want to talk about. It's essentially a record of the galaxy's star formation rate as a function of time, all the way from the Big Bang to the time of observation, right? Pretty simple. Why is this important? Because I feel like it holds complementary information in a lot of ways to what we think about when we think about like initial conditions to merger tree to final observables. So let's ask the question of what do we hope to learn? Sorry, Steam's jumping in the background. Cool. It's good that I'll come back to it. All right, excellent. So what do we hope to learn? Well, very simply, we want to know what's going on, in the sense that starting from these relatively simple, well understood initial conditions and with a set of physical processes, we both end up with like this incredible diversity of galaxy populations, but we also end up with all of these emergent scaling relations when we look at summary statistics that describe galaxy populations. So how is the same sort of set of physical laws giving rise to both of these things? We want to know that. And so if you go and look at the physical laws, again, from this time scale perspective, right, you're looking at like, you're thinking of the characteristic times over which these things act and influence star formation in galaxies. You see that they cover many orders of magnitude, that they heavily overlap and influence each other. So studying them in isolation becomes really difficult. And we don't know what the relative contributions are to overall star formation in galaxies. So this is the ultimate problem we want to solve. Can we solve this with star formation histories? That remains to be seen, but like that's sort of what I want to motivate in this talk, right? The part of the reason why this is even remotely tractable is the fact that we have access in our galaxy spectra to a bunch of different spectral features that are all sensitive to different time scales that sort of span this range. And the hope is that we can somehow connect this to the physics, right? Like that's the ultimate. And we might not want to do this for individual galaxies, but more for ensembles of galaxies for which we have distributions of these and their covariances. And maybe that kind of full data set of information might be able to constrain the physics. Okay, so that's what we hope to do. Now, what can we do, right? This might be a subset of what we hope to do, but let's see how far we can stretch it. So a very incomplete list is that like if you have star formation histories, all the things that depend on star formation histories like stellar masses, star formation rates, and downstream quantities that you use to make mass functions and cosmic star formation rate density estimates and all of those things automatically become better if you can constrain your star formation history well to begin with. You can talk about timescales of quenching and rejuvenation and all of these sort of once in a lifetime or like a few times in a lifetime events. Or you can talk about burstiness or like short timescale stochasticity that happens due to supernova feedback and the likes. You can maybe connect that to feedback and baryon cycling, and you can talk about how this correlation between galaxy structure or galaxy environment and how it forms stars over time, right? There's definitely more, but like, come talk to me. Okay, and the way we want to do this, right? So it's sort of like breaking this problem down into 3 parts. One could say that what we can do is start with our models or simulations, forward model all the way to our observations, and directly compare and sort of figure out what's the best model parameters that match the observations. I'm trying to break this into 3 problems. One is of like, how do we infer, sort of how do we connect star formation histories to observations and do that inference problem. The second is, how do we connect star formation histories to the physics in these analytical models or cosmological simulations and sort of get an insight. So what I want is to have that as a latent space of sorts that contains all the information that we want to probe. And the reason I want to do this is because A, it's interpretable. Star formation histories sort of give you like a physical picture of what this thing's been doing over time. But also because there's a small domain shift between what we can get from observations and sort of all the modeling assumptions and selection biases and all of the things that go into that, and how things in the simulations also depend on resolution and box size and all of those things. And so there's this small domain shift, and like having the latent space and looking at things there sort of helps understand the bit better. Okay, so that's the 3 things. I'm going to be briefly going through all 3. So 1. This is fairly standard. I really have to thank John and Eric and folks who sort of set up SED fitting. And so the way this works is we start out with some kind of spectrophotometry, and we say that we want to fit this with our model and get some posterior distribution. This posterior distribution corresponds to some posteriors on the physical parameters. And then in that is whatever parameterization we use to talk about the star formation history, and then from that we can construct a curve of star formation rate versus time. There has been a lot of discussion during this workshop, especially the last few weeks, on what kind of parameterization can we use that can capture the full diversity of star formation history populations, but also have enough physical information to sort of constrain this and not give like 3 decks of uncertainty for every galaxy. So is there a middle ground, right? Andrew Heron talked about like a min flex versus max flex model, and is there something in between? So that's sort of what I want to motivate, that let us, for a moment, think of a star formation history as a Gaussian process. What is a Gaussian process? It's essentially an infinite dimensional Gaussian that has 2 properties. One, it has a mean. So essentially like every dimension in this Gaussian corresponds to 1 point in time, right? And the mean at every point in time essentially tells you what the mean shape of the star of the history is. And it has a covariance that tells you how the star formation rate at time t and t prime are related to each other. That's it. That's all you need to specify a Gaussian process. So graphically, this is sort of what a prior looks like for this GP. You have a sort of mean prior for the star formation rate versus time. And so this is sort of like the space of all functions. And you have a covariance function that tells you like how star formation rates are correlated with each other. When you have observational constraints on this, you can condition the GP on this observational data to get constraints and obtain a posterior on the star formation history, right? So that's the basic framework. So given this GP characterized by mu and sigma, the rest of the talk is essentially going to be how we write out the mu and sigma and what that can tell us about the physics, right? So first, the mu, right? So this is the dense spaces method. This is sort of parameterization that we've been developing, where we talk about a galaxy star formation history's mean just using these 3 parameters: the stellar mass, which is the integral under the curve modulo some mass loss, the star formation rate at the time of observation, and a set of Tx parameters, which are essentially the look back times at which the galaxy forms some quantiles of its mass. So with 3 parameters, that's essentially the times when it formed 1/4, half, and 3/4 of its mass. And these parameters essentially put constraints on the shape of the star formation history by saying that, like, if two of these are close together, it has to form the same amount of mass in a shorter amount of time, so the average SFR has to be higher, and so on, right? So these are integral constraints. So this does really well with a really small number of parameters at describing the shapes of star formation histories across a range of simulations and local CMDs and so on. And it can do a lot even with a single parameter. So with a single parameter, which is T50, the time at which it forms half of its mass, you can still have all of these, like the rising, the steady star formation, the young quench, the old quench, the post-starburst, the rejuvenated galaxy, right? You can play around, and just with those three parameters, you can recover, in essence, the broad strokes of all of these galaxy populations. So great, it's flexible, and then you can tune the prior, right, which is described by like this Dirichlet distribution, to have as much physical information as you want. So you can either make it uninformative and try to put in like a flat SFR prior over time, or you can tune it to a simulation, or you can say that there is no such thing as an uninformative prior, so I'm going to choose something that I think makes sense. And so when we now apply this with the same prior, right, to a bunch of observations, you can see that with rising mass going from 10 to the 9 to 10 to the 11 and a half, or with rising age of the universe going from redshift 3 to 0.5, you can now recover the sort of trends of like young, like not very massive galaxies have sharp rising star formation histories to old massive galaxies quenched some time ago with the same prior, with the same parameters, right? So that's the sort of flexibility that this method gives you. And because it does that, you can now do a whole bunch of science. I just want to advertise stuff that some students have been doing. So Caleb Lammers has been looking at the effects of AGN feedback in manga galaxies and finding that the star formation histories tell you that it's not that the quenching time scale is different, but the time since quenching is what's different between the AGN and the control. Juan Alfonso has been looking at the SFH morphology connection and trying to use CNNs the way John does to see if there are parts of the morphology that tell you something about the star formation history. And Kate Gould at Dawn has been doing this really systematic analysis of priors, right? Because we said there's no such thing as an uninformative prior, to figure out what's going on, what's the best way to identify quenched galaxies at higher redshifts, sort of what's the amount of stochasticity and all of that. So this is all really cool stuff, and please talk to me afterwards if this is interesting. But like, in addition to those sort of like summary timescales, like the quenching timescale, can we go further? Can we get more information out of this, right? And so because when we talk about supernova feedback or mergers or something like that, we tend to think of like repeated events that happen many times in a galaxy's lifetime. You want to then maybe look at the power spectra. So you take the Fourier transform and you find the power by averaging out over the phase information. And you see that while the star formation histories in all of these different simulations, so we can't do power spectra from observations yet. I'll get to that. But in the simulations, they have broadly similar trends qualitatively in the star formation histories with increasing stellar mass. But if you look at the PSDs at like a range of time scales, they can show quite different trends in what they're doing. So if you sort of make a plot of, I take one simulation, TNG, and I take slices at different times, and I look at the power spectrum slope versus normalization, you get these sort of trends with increasing stellar mass. And you can try to come up with some kind of physical theory for why this might be happening. So like, as AGN feedback kicks in and quenches galaxies, maybe that's what's responsible for this trend, right? So that seems cool. Like, this might be a promising way of using a simulation to connect, physics to signatures in the PSD. All right, but before we get to that, let's just check a few other simulations, see if they are all doing qualitatively the same thing, right? Because that would be nice, some consistency. So when I saw this plot first, I was kind of horrified, right? They're all over the place, they span this huge parameter range, nothing matches. Then, as I thought about it, I was kind of happy because this tells you two things. One, the simulations are very sensitive to both numerics and physics. in the space of star formation stochasticity, right? So if we can get observational constraints in the space, that would be amazing to understand what the simulations are doing right and wrong. Great. So how do we do that? And that brings me to the covariance of the Gaussian process. So the covariance is something I'm going to define as some function of t and t prime, the separation between star formation rates at 2 times, and some parameters that give you like a parametric form of the autocovariance. And we wanted to take a physical model that sort of describes the PSDs of galaxies well, and Sandra Takela and John Forbes and Neven Kapla have been doing some really cool work on this, sort of extending the regulator model to make this thing with 3 timescales that has essentially like an effective long, intermediate, and short timescale built in that sort of describes this analytic PSD. And so Josh Spiegel and I sort of took this and we used the Wiener-Khinchin theorem to bring it from Fourier space to autocovariance space in real time, so just as a function of separation. And the really cool thing about an autocovariance function is it fits in to a GP, which means you can now draw from it. So you can say that like this is my physical GP, physical kernel that has those timescales, and then make a draw that essentially makes realizations of star formation rates corresponding to that structure of autocovariance. And you can forward model that further to get to spectral space. Right? So this provides us a really powerful tool to go from timescales to star formation histories to spectral features. And the really nice thing about all the people here is that they're really interested in things like simulation-based inference. So now you can use all of these spectral features that I talked about at the start of my talk to see if you can get constraints on these timescales that go into the model. And so it looks, at least from our experiments, that with as little as 30 galaxies, you can start constraining the overall amount of scatter and the timescale that sort of let you get the shape of this ACF. And remember, because that's related to the PSD, these constraints will translate directly to constraints on the power spectra. So this is still work that like I've been doing recently / during this conference. So I'm really happy for all the input I got from people here. All right, and going back to like connections to physics, this was again a project that I started here. Sitska helpfully compiled star formation histories for a bunch of these Camels galaxies, and I think Paco might have talked just a little bit about them. And we essentially said, so if we take a sample of 100 galaxies between 10 to the 9.5 and 11.5, and we compute just their shape, so not even putting in any covariance information for now, just their shape, and feed that into a simulation-based inference method, can we predict anything? And I didn't really think we could do anything with the cosmology, and I didn't care. I was more interested in the feedback. And so it looks like we can get at the supernova feedback. AGN feedback doesn't seem to be doing much in Camels. But it also looks like we get some constraints on cosmology from information that we are essentially putting in implicitly about the mass function and about the shapes of the star formation histories. So I'm not concerned about just being able to make the prediction. I kind of want to go back and understand what's going on. So in the case of omega m, it seems to be the depth of the potential well, and then the resulting halo accretion rates that seem to be driving sort of changes in the median shape of the star formation histories, and therefore there's some sensitivity there. For the supernova feedback case, it essentially seems to be decorrelating star formation rates. So like in the autocovariance function, it's essentially like reducing the correlation time. And that seems to be what is driving sort of the rate at which gas is consumed, and that's changing the shape of the star formation histories. So like there's these like different non-degenerate ways in which the star formation history shapes and distribution changes as you change these parameters, which makes it a powerful tool to actually do inference, but also just learn more about how feedback affects star formation. Right? So this has been really fun to do. And I also want to advertise stuff that a student, Yunjin Shin, has been doing with the Agora simulations. She's been looking at how changing bulge to total or how changing stellar feedback in a single disk galaxy, like systematically keeping everything else the same, changes the power spectrum. So that's again like And she's now looking at both the spatial and temporal power spectra. So she's finding that bulge to total changes one and feedback changes the other. So that's also like something interesting to think about. All right, finally, just going to touch on the domain shift because I am not the expert here. And there are so many people here. Alex gave such an amazing talk on domain adaptation, so I would refer you to that instead. But the basic point is this, that simulations and observations currently don't quite live on the same space when it comes to star formation histories. From the simulation side, this could be because of resolution and like just the simulations not having converged. From the observational side, it could be selection biases, modeling assumptions, priors, whole bunch of things. For that whole bunch of things, I essentially listed some of them during my CD fitting tutorial at like an earlier point in this workshop. And basically like so many people are working systematically on different parts of this. So like John was talking about dust, for example, and that was great. Like we sort of need all of that to come together to better understand like that phase of the domain shift. And in the simulation side, stuff like camels really allows us to understand what's going on in combination to resolution studies in terms of like why simulations might have a certain shape for this transformational state. Finally, I just wanted to mention again from the tutorial that there's a whole bunch of different ways of doing checks to make sure that you're doing okay when you're getting star formation histories from observations or when you're comparing them, right? So one is posterior predictive checks. Whenever you derive something, make a prediction for something that you can see and see if you can predict that within uncertainties. When you're doing things with a certain code or a certain set of modeling assumptions, try varying and see what happens. When you're doing stuff with simulations, forward model it, see how well your forward model does in capturing the full distribution of the observations. And the last one's sort of vague, but it's essentially saying like, say you're getting individual star formation histories. If you make a mass function at a higher redshift using these, like you take everything back along its curve from like redshift 1 to redshift 2, is that consistent? Right? Like, or do you do something really weird? Like Sucheta showed this really nice plot where you take tau models and you try to just get the median star formation rate in a bin. It looks completely bunk if you use like a simple parametric model. So this is sort of like, they have different strengths and weaknesses, and I think people in this field, in this room, are being really conscientious about doing one or more of these, and I'm really happy about that. So last thing, I just want to advertise this thing called the Pan Survey SAD Forum. This is a safe space that we've been trying to create so that people can talk about state of the art in all these different ingredients that go into SED fitting. And if you have ideas for future topics that we can discuss, for things that you feel are controversial or that you would like more input on, please let us know. There's a link up there that you can join. There's a Slack that has like 250, 260 people who all care about SED fitting in some way. It's great. And we aim to do roughly monthly events, although we haven't done one this year yet. We'll get there. Yeah, so that brings me to the conclusion, which is that you can describe star formation history sort of using this Gaussian process formalism, where you describe the mean using mass SFR and TX, and you describe the covariance using this extended regulator model. And hopefully this provides a framework that allows theorists to talk to simulators, to talk to stats/ML people who talk to observers. So yeah, thank you so much. I hope we all keep talking to each other.
Thank you, Kartheik. Questions?
Hi, thanks for the great talk. So, Hao and John speaking here. So my question is about your experiment trying to use Camel's galaxies to constrain all the parameters. So what are the stellar mass ranges that of the galaxies in your sample?
Right. So we wanted to be massive enough that resolution's not really like, that your star formation histories are reasonably robust to resolution. And we wanted to be not so massive that it's affected by cosmic variance because the box is small. So we are currently, we tried 10 raised to 9.5 to 10.5 and 10 raised to 9.5 to 11.5, which is what this plot is for.
So 9.5 to 11.5.
Yeah, for this plot. But like 9 to 10.5 also does well on supernova. It does worse on cosmology.
Okay. So, well, we typically think that AGM feedback doesn't play a huge role unless you go to a massive regime, right?
So I tried a thing with just 10.5 to 11.5 because 10.5 is roughly where the black hole mass goes about 10 to the 8.5 in TNG, and that sort of kicks off the quenching by AGN feedback. But we didn't really find a signal even there, and I redid this with Simba, and in Simba you do find a correlation with AGN1.
Okay.
So, but like that's slightly different.
Okay, thanks.
Yeah.
Beautiful talk. There we go. Really nice. Reese Wexler, can you go back to that plot that has the comparison between all the models in that funny space?
Yes.
Yeah. So do you know something about the data in this space?
No, so that's sort of what I'm getting at. Like
Okay.
the hope was like we make this autocovariance function, and this
Yeah.
is essentially like a parametric way of describing this, which means that once we constrain this, we can slice it and like talk about the strength.
I see.
And then sort of, so we are at this stage where 4 toy models, like the red and blue here are, the red is like a Milky Way like galaxy, and the blue is a high redshift like galaxy. And so we can tell these apart and we can constrain the time scale. So the hope is we do this and we maybe combine it with like stuff John is doing for like doing dust properly. But like the thing is, these are really finicky signals.
Yeah.
So toy models are great, but like getting to observations is going to be a bit harder. So you need chemical enrichment and dust to be like properly accounted, and it's a work in progress. But like I hope to get to observational constraints.
Yeah, Pablo here. Yeah, I'm very interested in the SBI part, as I told you. Have you tried to run any like coverage tests or anything to validate that you're getting correct coverage, that your SBI is properly accurate?
Yeah, so I mean, I didn't show this, but like in, yeah, we've been trying a whole bunch of like variations of sort of what information we feed in, what mass range we use, what subset of simulations we use, whether we resample the thing, whether we give it in additional information in terms of like covariance functions, and some results seem to be robust while others are more finicky. So like ASN1 and sigma 8 are pretty finicky and like dependent on the exact things that you put in.
Yeah, I was asking because it looks like it looks biased. So I don't think it would pass a coverage test, but I don't know. Like it looks like AGN and ASN are.
Yeah. I mean, like, yeah, you don't really see I guess you see uncertainties on that. It's less visible here, but you're right. Like in terms of, how do I put it? There's additional information you can give it that would make it pass coverage, like the autocovariance functions. But like as it currently stands, it seems to be more sensitive to like certain regions of parameter space.
Thanks.
Yeah.
Can you go back to your I think slide 9?
Okay.
I keep doing that with the microphone. It was the timescales.
Yeah.
This one.
Yeah.
Yes. My comment is that it's very pretty, and I want to stare at it a bit more.
Thank you. Yeah, this was like that 2020 paper has a full table of like every timescale estimate in the literature that I could find, and this was just me trying to synthesize that information into a useful.
It's very nice.
Thank you.
Kartheik, very nice talk. This is Peter Beruzzi. Could you go to the slide showing all the postage stamps of all the different star formation histories?
Yes.
As a function of mass and redshift. I was just wondering if you could say a little bit about which observations were supporting rejuvenation happening, because it looked like maybe the redshift 2.5 and stellar mass of 10.0,
Yeah.
like all the UDS galaxies were rejuvenating. So I was just wondering, like, sort of, what about the observations was causing the models to have such a high rejuvenation fraction there?
Right. Yeah, I mean, okay, so I didn't get to go into detail in this during the talk, but these are Candles galaxies. So it's Candles galaxies in all 5 fields. So Cosmos, EGS, UDS, Good South, Good North. And so the different curves are essentially like there's one curve for each field. And part of the point of this plot was to see whether if we have enough galaxies in a given bin, do the star formation histories broadly agree in sort of what they're doing? So in the sort of like bins where we have enough galaxies, which is like on the order of 100, the broad trends do seem to agree. The redshift 2.5 stellar mass of 10 it's a slightly weird bin, partly because partly because there's not too many galaxies in that bin, but also because the UDS has like a few filters that we think make it more sensitive to sort of features that are responsible for like a sharp Balmer break plus recent star formation. So that's sort of causing that humped structure. So we still need to sort of run again coverage tests to see how much of that is strongly supported by the data. But like from this analysis, we just concluded that they're consistent within sort of uncertainties, which is that shaded region. So we didn't put too much trust into the rejuvenated population there.
Okay, hi, it's Laura Schultz. So very cool stuff, I really like it. But I was curious, like with inferring the star formation history from observations, have you compared to star formation histories non-parametric from full spectral fitting, like PPXF, starlight, and these things? How do they look like?
So we haven't done that comparison, like not to full spectral fitting, because there's just, when you get to that kind of information content, like there's so many factors that I need to consider that it becomes like an involved analysis that I want to tackle at some point but haven't had the time to. I know that Joanna Wu, for example, is doing an analysis where she's been comparing Firefly to PPXF to Starlight to sort of these mock truths that she gets because she takes TNG and like forward models the spectra. So that would be like a useful analysis. We did compare to things like Camilla Pacifici has another non-parametric method, Joel Lija has prospector. So we did compare to those star formation histories and we generally find good agreement. So that's a paper that I'm working on at some point.
Thanks.
Thank you.
And the last question by Johnson. Sorry,
really amazing talk. Two questions. So first, like, are the curve on your T-shirt star formation history?
I wish.
Okay.
Yeah.
And then the second question is like, I know you also look into like the neural ODE or like hidden like Markov models.
Yeah.
What are the pros and cons like using GP like versus something more flexible?
Okay. Yeah. Excellent question. So yeah, like there's always been this question of like what's the best way to represent a star formation history, and like I've been trying to think about this for a while and I don't think I have an answer. I have been recently playing with stochastic differential equations as a way to represent star formation histories. Currently, the major limiting factor seems to be convergence. So essentially, the fact that star formation histories are roughly logarithmically sensitive in time to observations makes it a problem that's ill posed to like anything that treats it as a field. And so treating it as a GP means, so GPs are great because it doesn't care about sampling. It can be as sparse or as dense as you want it to be. And so that's the thing that's currently winning out. But yeah, thank you. Also, thank you for all the questions. This was great.
So thank you, Kartheik, again.